Hey everyone, and welcome to this explainer. Now, if you are a JEE-focused learner, you already know the drill. Algebra can sometimes feel like this, well, an endless pile of disconnected formulas that you just have to memorize. But today, we are completely changing that approach. Think of this explainer as your ultimate structural blueprint for mastering mathematical patterns. We're going to look at sequences and series not as random, messy equations, but as beautifully engineered structures.
All right, let's jump right in. Mathematics really is a lot like architecture. We aren't here to just read a textbook and hope it sticks. No, we are going to build our understanding entirely from the ground up, so you can conquer literally the most complex equations you'll face in your entrance exams. See, by viewing individual terms as points in space, and the common differences or ratios as the structural beams connecting them together, you start to develop this deep intuition that brute force memorization simply cannot match. So, here is our game plan for today. We'll start with 1, base mechanics, then build up our 2, 3 core pillars, and construct 3, the architecture of averages. After that, we'll equip you with 4 pro-level tactics, before finally running through 5, execution and hazards. Okay, section 1, base mechanics. Let's lay down that ground floor. Because before we can build anything, we really need to clearly define our raw materials.
It is so easy to mix these two concepts up, right? But the distinction is super clean. A sequence is basically an ordered list of numbers that follows a definite rule. Think of these as the individual points, the specific coordinates of our structure. A series, on the other hand, is the aggregate sum of those terms. So if a sequence is a collection of plotted points, the series is the accumulated area underneath them. Grasping the structural difference is absolutely crucial before we actually start compounding numbers.
Moving right along to section 2, the 3 core pillars. This is where we examine the real load-bearing columns of our mathematical architecture: arithmetic, geometric, and harmonic progressions. First up, we have the classic arithmetic progression, or AP. It's essentially a linear staircase. Each step goes up by a constant difference, which we call D. But honestly, the real takeaway for your exams isn't just knowing the nth term formula. It's the tactical substitution. When a problem throws unknown terms at you, use symmetric substitutions to immediately eliminate variables. Say you have 3 unknown terms. Don't use A plus D, and A plus 2D. No way. Instead, use A minus D, A, and A plus D. Add them up, the D completely vanishes, and boom, you have a direct path to the solution. Next up is the geometric progression, or GP, and this brilliantly shows the contrast with an AP. Instead of a linear staircase, a GP represents exponentially scaling through a constant ratio, R. It rises so rapidly. And just like with AP, there is a master tactic for substitutions here. The absolute best 3-term substitution in a GP is A over R, A, and A times R. Why? Well, if a problem gives you their product, multiplying them instantly cancels out the R, leaving you with A cubed. It unlocks the variable in seconds. And our third pillar is the harmonic progression, HP. Conceptually, HP is basically the reciprocal reflection of an AP. If you take the reciprocals of an HP, you get a perfectly straight AP line. But here is the massive system warning that you need to remember. There is absolutely no direct sum formula for an HP. Period. Doesn't exist. If you're asked to find the sum of an HP or solve complex HP terms, you must always convert the terms to their equivalent AP, solve it in that space, and then map your answer back. Let's consolidate all of this into a single organized matrix. Think of this as your mental dashboard. You've got the structural core for each, constant difference, constant ratio, reciprocals. You have your nth term formulas, the sum formulas, and of course that glaring blank spot for each P, plus your optimal substitutions, all in one spot. By shifting from visual graphs to this kind of recallable comparative data, you're literally wiring your brain to instantly categorize any sequence problem you come across. All right, pillars are firmly in place. Let's build the roof. Section 3, the architecture of averages. This is where we see how these individual sequences interact with each other. So, we have 3 distinct types of mathematical means. The arithmetic mean, or AM, is like a linear scale balance. It finds the exact middle weight between 2 points. The geometric mean, GM, is all about area. It finds the side length of a perfect square whose area matches a rectangle of sides A and B. And the harmonic mean, HM, that represents crossing vectors, which is super useful when dealing with rates. Understanding these distinct geometric realities really helps you visualize what an average actually represents in different mathematical spaces.
But, how do you actually know which one to use when you're staring down a really dense JEE word problem?
Well, just follow a simple decision tree. Ask yourself, what kind of interaction exists between these quantities? If you're adding things up, like marks or distances over equal time intervals, go with the arithmetic mean. If the problem involves compounding growth or population scaling, you need the geometric mean. And if it asks you to average rates, like speeds over equal distances or resistors in parallel, instantly switch to the harmonic mean.
Now this right here is where the magic happens. All three means link together into a single geometric truth. For any positive real numbers, the arithmetic mean is always greater than or equal to the geometric mean, which is greater than or equal to the harmonic mean. It's the core inequality. Furthermore, we get this golden result: GM squared equals AM times HM, meaning the geometric mean is literally the geometric mean between the arithmetic and harmonic means. This structural relationship is incredibly powerful for finding minimum values, and it saves you from having to use complex calculus.
So, we have a really solid structure now, but basic structures won't survive a hurricane, right? It's time for Section 4, Pro-Level Tactics.
Listen up, because this is a crucial warning. Standard formulas are really just the prerequisite. If you rely on them alone, they will fail you in JEE Advanced. The examiners already know you have the formulas memorized. What they're going to do is test your structural integrity by combining them or burying them in crazy complex fractional series. You absolutely need elite, pro-level strategies to dismantle these questions.
Let's look at the pro tips dashboard. First, you have the arithmetic geometric progression, where terms are product of an AP and a GP. But the real game changer I want to highlight is the telescoping sums tactic, which you often get through the method of differences. When you face a truly terrifying fraction, your goal is to express the general term as a difference between two consecutive functions, like f of n minus f of n plus 1. Because when you add the series together, all the intermediate terms violently cancel each other out in a chain reaction. It leaves only the first and last boundaries. It is just such an elegant way to collapse a massive problem into a quick two-step solution.
We are in the final stretch now. Section 5, Execution and Hazards, because even the best architects need to know exactly where the sinkholes are before they start pouring the concrete.
Let's rapid fire through the 5 most dangerous traps students fall into. 1. The HP sum trap. We talked about this. Never, ever apply a sum formula directly to an HP. 2. The infinite GP boundary. Before you use the infinity sum formula, you have to verify the absolute value of R is strictly less than 1. If it's 1 or more, the series diverges and just explodes to infinity. 3. Using AM/GM for negative numbers. That inequality strictly requires positive reals. 4. Mean counts. If a question says insert n means between A and B, your total number of terms is actually n plus 2. Don't mess up that index. And 5. The decreasing AP assumption. Remember, your common difference D can be negative. Never just assume a series is always going up. Now let's actually model how a master architect executes a solution. Take this problem. The AM and GM of two positive numbers are 5 and 4. Find their HM and the numbers. Step 1. Extract and map. AM is 5, meaning A plus B equals 10. GM is 4, meaning A times B equals 16. Step 2. Apply the golden rule. Don't even try to solve for A and B yet. Use the structural relation. GM squared equals AM times HM. So 16 equals 5 times HM. HM is instantly 3.2. Step 3, solve via quadratic structure. Just use the sum and product of roots to form the equation x squared minus 10x plus 16 equals 0. The roots are 8 and 2. It's fast, it's error-free, and it's totally structurally sound.
And that brings us to the ultimate master blueprint, the architect's cheat sheet. Seriously, take a mental snapshot of this. It aligns everything we've just discussed, the formulas, the means, the conditions, and the substitutions across AP, GP, and HP. But always, always remember to do that final clearance check. Verify your limits, ensure your variables are positive reals for inequalities, and actively scan for those telescoping structures before you ever attempt a brute force calculation.
Well, we've laid the foundation, we've raised the pillars, and we've built the roof. You now possess a really deep structural understanding of sequences and series that goes way beyond simple rote memorization. These formulas are no longer abstract numbers on a page, they're literal tools in your belt. So I'll leave you with this final thought as you head back to prep for your exams. You have the blueprint. How will you build your solution? Keep building, keep learning, and try to approach your next math problem not as a hurdle, but as a masterpiece just waiting to be constructed. Catch you next